thank you for the presentations made by all of my predecessors. It will be a tough act to follow because I have to start with a small disclaimer that by no means I'm an expert in encryption. This presentation should be done by one of my colleagues, but due to logistical reasons, I will try to do my best and explain at least the theory behind the hardened encryption that we are trying to implement or develop in Arcadian. So I won't go in and this is my disclaimer, I won't go into so many technical details like, for example, Giacomo did, but I'll try to explain, as I said, what's the idea behind the technology and where are we implementing them. So yeah, let's start with a little bit of encryption theory, which basically when we talk about attribute-based encryption, we always face the small let's say issue that usually encryption in its first context, when you think about it, it's a one-on-one relationship, meaning that either you encrypt and decrypt everything, or you basically don't. So it's always a one-on-one relationship, and this relationship is dictated by the identity of the encryptor and the decryptor. So you always have to keep in mind both actors on both sides. This, of course, is not really ideal in all scenarios. With things evolving, it's becoming apparent that it's less and less effective and less ideal, because with modern scenarios, we would like to have the possibility to have, let's say, a middle ground when it comes to decrypting and accessing data. Yeah, this is, as I said, a little bit of theory. You have to, when you are encrypting stuff, I will glance over this. It's a lot of boring, let's say, theory. But what I wanted to say is that when you are encrypting, you have to specify policies. You have to specify ciphers. You have to specify keys. And I deliberately made these slides very similar one to another, because I want to show that when you are doing the ciphers and the keys, the policies for these two, basically you are switching two things around that need to match in order to have the encryption and decryption working on either sides. This is just a basic image of or representation of how this stuff works. Basically, somebody or something generates the data. You have to think about what kind of data it is. Think about the attributes that you want to apply over it. Based on this, you specify the access policy, you apply it, and then encrypt it and send it. On the receiver side, basically just the arrows turn around, and you go the same process. The same process, but just in reverse. So it's a very linear process, and and you can also say very basic in its ideation. But why do we want to why do we use it, and why is this not so perfect for us? Because we want to use, we want to access we want to access with different policies to different bits of data or to different sets of data. So instead of having this, and I hope there are no mathematicians in the audience, because I will say something very unmathematical, but instead of having a very linear process, we want to have a kind of a matrix where we have different access policies and different actors accessing different kinds of data. So we want to have a mix and match where we can do different scenarios and different people with different different actors with different levels of access in the decryption stage. But of course, this with it brings some very important questions that we need to address when we are developing the system. Is first of all, yeah, we understand encrypting the data is a security measure. Not all data is for all eyes, and that's why we use encryption. But of course, with this mix and match that we want to do, this brings the question: who will be deciding who has access or who has the power of decrypting the data? Who has the right rights? Who has the right privileges? Is the person or the actor deciding this even the right person? And basically, it's a multi-parameter, let's say, question. If the right people have the power of encrypting, if the right people have the right power of decrypting, are we doing it? Are we sure that we are doing it in the right way? Are we sure that the right person manages it? Yeah, how do we answer all of this question is with multi-authority encryption. So we are going now one step further in the, let's say, complexity of the system. Yeah, as I said, the idea here are exactly answering the questions that I posed earlier. Is can we distribute the authority of delegating the decryption power? Can we have basically, can we have more, let's say, more people in charge of distributing this power, more people? And when I'm saying people, this can be, of course, a system. Can we have, well, basically, can we distribute the power of encrypting and decrypting? And by this distribution, do we can we make it that some people can only access parts of the data that they are actually, let's say, allowed to access and view? And of course, the answer is yes. This is of course, the answer to this is the multi-authority attribute based encryption, where the picture before I mean, the picture now is very similar to the one before, but it changes up here in this three clouds, which, I mean, the clouds have multiplied, meaning that we have multiple authorities setting different, let's say, attributes or different parameters of accessing to different stuff. So we have an authority for administrative privileges, we have an authority for users, we have an authority for services, we have an authority for whatever kind of data we might imagine to need in our system. The process of encrypting is still very linear, but as you see below, because we have several authorities, then we can mix and match and make combinations of types of access and access policies, and each of the authorities has to have its say in determining the access policy in order to have the system working, so that we can be sure that the right encryption / decryption is applied to the data that we want to share or even store for later use. Why we do this? As I said, all the nice properties that we already had, but with this we get this variability in the access structures or in the access policies, meaning that we can be as strict or as lenient as desired or as needed, and we can involve different, let's say, levels of access to the decryption possibility. In Arcadian, we are doing this, but we also trying to involve different kinds of technologies in order to facilitate or in order to add more features and more capabilities. One of them is blockchain. We challenge ourselves if this can be used, and of course the answer again is yes. Why is blockchain nice? Because blockchain is inherently a decentralized technology, meaning that but while it's decentralized, it's still verified by multiple authorities. Again, the words are repeating itself. It can be public, so access is easy to the keys, but not to the policies. And all the blockchains, all the actors contributing to the blockchain are of course contributing to its verification and validation, meaning that we have the proof of the blockchain, so it's verified by different authorities, but we can do this in a trustless manner. Again, this is the software side of things. We are trying to involve also modern hardware verification technologies. So we are doing we are also implementing the hardware root of trust, and this is the hardware side of all of the three. As Giacomo mentioned earlier, we have the use cases. The hardware root of trust is part of two of them. One is the medical, one is the mobile device. With the eSIM, we have a tamper-resistant and a hardware configurable device that enhances the system with one more level of let's say security features. It's tamper resistant, as I said. It's in the case of tampering, it can also be reconfigured, so it's a form of active let's say protection. So we incorporate all of this stuff just to be sure that the right and only the right let's say set of eyes can view the data that it's allowed to view. Going even a step further, and I'm not counting the steps anymore, I must admit it. We are doing also functional encryption on the data. This is a pretty novel, and I will say a pretty novel field of mathematics, because we are not only encrypting with specific algorithms, but we are actually using mathematical functions to encrypt and decrypt the data. But what this allows us is that, and this will be apparent in the next slide, when we are encrypting the data, we are using mathematical functions. Usually these are vectors or polynomial functions. And this allows us to work on the data and do statistical analysis on the data, or draw out statistics from the data that we have without having it decrypted. So, for example, if somebody in a case, and I apologize, I don't have it on the top of my mind right now, but if we need to do some kind of analysis on the data that is where the data itself is not so crucial, we can still do it without decrypting. Yeah, as I said, prominal are in this case the most useful are the polynomial schemes or quadratic schemes. As I said, this allows us to do a lot, or not a lot, quite some statistic or quite some data quite some data work still on data that is encrypted, so there's no need for decryption, which again brings also another level of privacy to the data. And the nice thing is that this can also be, again, a mix and match between attribute-based encryption and functional encryption. So we don't need to have the strict guidelines, or we don't have to think about the, let's call it, end user when we are already encrypting. But we can do this further down the line, and this gives us way more flexibility and way more confidence that our data is actually secure. I will conclude with I'm almost at the end. We do this. The example of functional encryptions to keep in line with the graphs is that we can do sensor data. We can use, for example, just the sensor data without decrypting it. So there is no, you see at the end, there is no decryption state, but the work can still be done even without decrypting the data. Conversely, I mean, conversely to the other techniques that were presented earlier. Yeah, I've basically presented this slide while I was talking. The benefits of this is that we can do computation on the encrypted data without actually decrypting it, meaning that we can, for example, in our case in the project, work on communicating with the sensors that are actually inputting it without decrypting the data that the sensor is feeding into the system. Where in Arcadian is this used? As I mentioned earlier, this is in the medical IoT use case, where of course it goes without saying, patient data is a very sensitive topic, and we need to be aware of what kind of data it is, who can access it, who cannot access it, which is even more important. And the other one is, and this one was also mentioned, I think, in the first presentation, the drone-based surveillance. Again, a lot of sensitive and personal data when we are doing images, when we are doing recognition of faces and people. So it's important that we can still control and work on the device, with the device in some cases, without actually looking at, for example, the images that are being fed into it. And with this, I will conclude my presentation. As I said, I'm not the specialist in encryption. I'm not mathematician enough, but I hope that everybody got the feeling of what can be done with modern encryption, let's say strategies and I hope that I brought over the idea that it's no longer a one-on-one, let's say, relationship as it was